we know, and it's equal to 43.335 kilonewton. When we make a round up to 3 figures after the point. At RB, we have 36.665. Yeah. At mid-length of the beam, the question is, what are the shear forces? What are the bending moments? What does this imply? That you calculate either from the left or from the right. That's up to you, but you have to take into account all the forces acting upon the beam. I'm just going to put it like this. For instance, now, all the force acting upon the beam, which means either all this part you have to take into consideration, or this part, depending how you calculate. You can calculate from left of right or left. The result will be exactly the same. You just might have a sign difference, but that does not matter. The absolute value must be correct. Yeah? So if you look from right to left, what do we see? We see again a rectangular shape and a triangular shape. Yeah. What forces do we see? From this rectangular shape, you have what? You have a resultant force acting at mid-length, meaning at 1.5 meters. What is the force in value of the resultant force, which is the basis, which is 1 meter, multiplied by 30, and it equals 30 kilonewton at 1.5 meter. From your rectangular part, again, yeah, you have at 1/3 here of 1 meter, you have the resultant force of that triangular part acting upon your beam, which is equal to what? The base is 1 meter. What is in this case the height? The height is half of what you have here. We will reason that later on, but now its logic is half. It's all in symmetry. Yeah. So it means in this case it's 10 kilonewton. Yeah. Multiplied by 1 meter divided by 2 equals 5 kilonewton acting upon this beam. How do you calculate the shear forces? The sum of all the forces, implying 36.665 minus 30 minus 5. And there you have the result. That's it. How do you calculate the bending moments? Exactly as you did before. You put yourself virtually in the mid-length of your beam, there where you want to do your calculation. And you look at all the forces acting upon the beam, meaning 36.665 over a length of 1 meter, 30 kilonewtons over a length of 0.5 meters, because it's only away from you for half a meter. And then you have 1/3 of a meter, you have the 5 kilonewton acting downwards. Just take again into consideration the sign convention. You have here a negative or positive if you like, but then this one is negative. You sum it up and you get your bending moment. And then what do you have as a bending moment, Freek? What did you calculate? I give you some time. Go ahead. Okay, Jules, what I can do if you don't get it yet, I can't stand still too long with those. We can always make an appointment in class after the online modus. I think next week is still online. I propose you'll all get into detail of the exercises, and then we make an arrangement, an extra course like a monitoraat in school, and then we can draw it on the board, and then I will re-explain. Okay? Freek. Okay, perfect. Freek, did you calculate the bending moment? As you were perfectly fine with the reaction forces, I guess that is the same principle. Are you still calculating, Freek? Or somebody else? You didn't get it yet? You're still calculating. Yeah, this is exercise 5 still. So if you position yourself in the middle of the beam where you want to have the value shear force and bending moments, you look at all the forces acting upon, and you multiply all the forces with the respective arms. So reaction force RB multiplied by 1 meter, as it's 1 meter apart, RB. 30 kilonewton, base is multiplied by height over 1 meter at 0.5 meters. And then 5 kilonewton of the triangular shape multiplied by 1/3 of 1 meter. And then just take the sign convention into consideration, and then you get a result. What is the result? $20, very good. Bending moment 20. Yep, correct. So the bending moment, I'll put it here. The bending moment at 1 meter, you can calculate as what? The first moment, which is 5 kilonewton multiplied by 1/3 of 1 meter. Yeah, plus or minus as you wish. If you take this all plus, you have to take the last one minus. Yeah, 30 kilonewton multiplied by 1/2 meter as an arm minus RB multiplied by 1 meter away from you. You can also calculate it from left to right as you wish. The result is the same. Okay, that's how you come to it. But making an equation, knowing what a moment is, I suppose you should know in the second year of this school. Yeah. Okay, another exercise. No? Okay, what I explained last week as well, because that's the only difference with all the other exercises, triangular shape thing. Yeah. So I repeat it once again, as I did last time. Hopefully it helps for those who might not have been present. Then please note this then now. If you have a triangular shaped load, yeah, like we had in this exercise, the length is in this exercise 2 meters. This height was how much? 20 meters, 20 kilonewton, I guess, at this position. And you want to know what is this height here at a mid-length at 1 meter in this case. Yeah. What you need to know that if you take this as A, for instance, and this as a B, for instance, B, and you want to know X, this height at 1 meter, yeah, you need to know that the ratios are the same. Why? Because it's a linear line. A linear line, the way it heightens is always with the same value. So it means that ratios are the same. That's mathematics. Meaning that what? B over A or A over B, yeah, equals, oops, why it doesn't work here, equals what? X over 1 meter. So if you take here 2 meters and you want to know X over this distance, 1 meter, The ratio is the same, huh? That's how you get to X. And that's why I got to 10 kilonewton. That's basic mathematics you should know before starting here in school. Yeah. And this is the only difficult part. Nothing more, nothing less. The surface of a triangle is basis multiplied by height divided by 2. And the thing that I give you as information is that for a surface like this, the center of gravity is at 1/3 of the entire length taken from here, 1/3 from here, or 2/3 from the other side, of course. There you put your center of gravity. So if you want to translate it to a resultant force, is base multiplied by height divided by 2 at the location 1/3 from the highest part. That's it. That's what you need to know from this type of distributions. Okay? But that's basis. And that comes back in those exercises. And this makes the exercise difficult for most of you. But it's only this, huh, that you need to know to solve it. Okay? Understood? Or still problems involved? So far, so good then. Somebody made some additional exercises? Who did it just to know? It's not a shame if you didn't. Okay, I'm gonna put you all out, huh? As moderators next time. I'm gonna take a print screen as well. My dear people, moderators who came back here. Yeah, I think it's all from but when we click on the link, yeah, I know you are. Yeah, but please be a bit polite to your colleagues, and you're not allowed to do things without my approval. Yeah? No, it does not start automatically. You need to activate it. I'm sorry. It's not an automatic thing that happens. How not to be a moderator? You can't. Then I need to swap the login. Ah, you did, Samuel. Okay, thank you for being so honest. Good. Thank you, Samuel. Okay, I like honesty, by the way. That's important value, a lesson in life, being honest. Good. Who did the extra exercises at home? Or you only made the exercises from the PowerPoint presentation, or somebody who did? No, it's okay, Samuel, no problem. Somebody who no secrets are being told, eh? So who made the extra exercises? Nobody? You only made the exercises mentioned in the PowerPoint presentation? Okay. It will become a lot, huh? For most of you then, huh? So try to make some, yeah. I will do an extra moment for exercises in school, but it will be, I will give you time. I will do it in module 2.2, somewhere in the beginning. Yeah, so you still have time to study after, because I think most of you will go with the DAR as well. Or do you prefer before the DAR or after the DAR? You can make it a joint effort on the DAR to make some exercises. Huh? Next week, not yet. I'm sorry, Jonas. Next week is still online, if I recall good, but the week after should be back in class. Both, if possible. That's possible too. We can do both. No problem. Yeah, but I will not put it in the last week. But if I understand well, you're having examinations in the last week of this module. So we put it the week before. Now the week after is still online. Then you have a week, Mr. Haga. Let me calculate. So we put it in week 5. Yeah, indeed. Week 5, the same time. Do you have other courses going on, or you have normally off in the afternoon? Normally no courses? Okay, so then we will arrange all of you if we can go back to school anyway, not next week, but the week after. Week 4, you have with Mr. Hage at school. Then we will put week 5 at the same time. We put a monitoraat of the exercises, okay? And we do one extra if necessary in module 2 too. All agree? Yes, somebody opposes? The date, please. Okay, 1 second. Let me have a look. Up. 1 second, because he did updates. Okay, so it means 23rd, it's still online. The 2nd of March, you have Mr. Hage in school, so meaning the 9th of February. In school, monitoraat. Yeah. Yeah, March, sorry, March. Well done, Constance. Yeah, I will put it on Blackboard. Yeah, and if it's nevertheless is a problem, let me know. For me, 1/3, 15 is fine, depending on your, I think you're all in school, so back we take the normal hours, 1:15. Yeah, very good. Wait, but then you promise me to work a bit, huh? Because you have to ask questions, huh? I need to be able to solve questions, just not, I do not understand all the exercises. That's not a question, huh? Thank you, Jonas. Perfect. Good. Okay, so be aware of this, what I just put on the screen. You have to use this for different other exercises in the future. The same principle is valid. So you need to know this in order to solve them. Yeah. Okay, so what do you get upon the exam? We just treated question 1 of the exercises. You will get 2 exercises upon the examination. And this is one of them. So you get actually 2 questions, and one is considered to be as a question A and B. So you can also translate to 3 exercises, and then some questions of Mr. Hage. And this is one of the 3 principles that you will get an exercise upon, what we treated last week. So you get a beam with a load. Most of the time it's just simply supported, but you have some others as well in the additional exercises, and you need to make a calculation. The extra Excel are on the presentation? No, in the Word document on Blackboard. Tristan? You have the minimum exercises incorporated that I can treat in class because I only have a restricted amount of time. But you have in the Word document on Blackboard, you have a lot of extra exercises available with solutions at the end. Okay? Good. Now, one of your colleagues asked me, suppose for this exercise, you need to trace the bending moments and the shear forces curves, because that's part of it. Huh? So one exercise is a beam calculation, meaning values for shear forces and bending moments, meaning as well the diagrams of shear forces and bending moments. Okay, so if we go to the diagrams of this particular exercise, yeah, how do you have to interpret the, so you have a reaction force here, reaction force there. You have a uniformly distributed load going like this, and you need to be able to calculate shear forces and bending moments. So what is it like? Just here, yeah. How do you start? No, this is same exercise number 5, just as an example, Simon. Just as an example, exercise number 5, how shear forces and bending moments evolve. Yeah. Shear forces is a sum of all the forces acting upon the beam. Yeah. Here you have a reaction force. And the reaction force at RA was how many? Let me have a look. 43.335. So you go from 0 to suddenly a value of 43.335. Huh? That's what you do. You have here a line, a surface, because you know shear force is the integral of the forces. You have a line here, which gives you a value, which is a positive one. But then what do you see? You end up with negative surfaces. You have to subtract this. So it goes from there, you go downwards, downwards, downwards in shear forces. Yeah. Then suddenly you will end somewhere here, and then you have back a reaction force, you go up. Yeah, that are shear force bending moments value. So you sum up all the forces. You can just point them out as well. What was the shear force value here at mid-length of the beam? We calculated it. How much was it at mid-length of the beam? Who has the value? At mid-length of the beam, it's how much? Who calculated the value? Exercise number 5. Yeah, positive or minus, Gillian. Yeah, it's indeed 1.67. Freek, you have to reconsider that one. Yeah. Yes, indeed. So you have here a negative value. Yeah. It gives you already an idea. So you go here down, 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 down. It gives you a negative value. Will it go further back down? If this is considered positive, this is considered negative. Yes, you go further back downwards until you reach at a point where you have a counteracting force upwards and you go back up. So that you can reason yourself. Yeah. Oh, why do I have... I don't know why. It's not working anymore. Switch to, press Windows key and space. I do not know what is. Okay, 1 second. Perhaps I need to use this again. Yeah, no. Damn it. Drawing. Yes, there we go again. No. Okay, can I do it this way? Yeah, but this is not that easy. Okay, so this you already know. Now, you know you have an evolution in between. My question to you, is this evolution linear or non-linear? Meaning curved or not curved? If you take the integral of a line like this, which is constantly linear, you see this surface, it's a curve indeed. You see this surface gradually, constantly diminishes, but not always with the same amount. When you have a horizontal line and you take the integral of a horizontal line, then you indeed have constantly the same amount of surface that you add on onto, and then you have a linear curve. This is a linear line. And now you have indeed a curve because your value here, yeah, this surface constantly becomes with a different amount, bigger, 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 bigger. Yeah. So what is the curve? You will have a curved line up to here. It's not a linear line. It's a curved line, as Marion Briac tells you correctly. Suppose we have the same beam, yeah, but then you have here a horizontal force. Then you see that the amount of surface always adds on with the same value. And then indeed, the line would have been like this. But now it's not correctly, huh? As you see, the value of the surface underneath the curve always adds on, but with a different value, a different amount. So it's a curved line. So if you do now the bending moments of this one, yeah, I'm sorry, but I one way or another, it doesn't want to use my tablet anymore. I will try later on to draw it again. The bending moments, what do you know? When you draw the bending moments, are there certain values that pops into your head, like this should be there, or some specifications? Where the shear force equals 0, what is your bending moment? What is the value? No, when the shear force equals 0, your bending moment is maximum, indeed. Yeah. So you can reason already that here, when your shear force equals 0, you have a maximum bending moment. You start with 0. You end up with 0, your moments. If you draw a curve in between or a line in between, if you want to interconnect the dots, is it a linear line or a curved line, non-linear? The integral of a non-linear line equals non-linear. So you will have a curved bending moment. Okay, let me now try to solve the problem. I think we have to restart one way or another. Clear. Why does it? Ah, there we go. Found it, I guess. Drawing. Yeah, there we are again, back in business. So what I wanted to tell you here, yeah, that's a disadvantage of online courses, huh? Why? Or is it, it's a line drawing? Why is it not working? 1 second. That I do not like. Why is it not willing to use my pad and my pen? Okay, let's do it differently then. Let me try to make use of the lines here. So suppose I will put two next to each other, two loads next to each other. This one has a distributed load over the entire length of the beam, nice horizontally. Yeah. So let's put it this and interconnect this one. You have a reaction force here. You have a reaction force there, which is of course 50% left, 52% right, because it's all nicely symmetrically. And then we have the same one as we just have now, like this, also uniformly distributed, but not in symmetry. We have the reaction forces like we did with exercise number 5. Yeah. Okay, evolution of the shear forces is what? Drawing. So we have here a reaction force at the start of your beam going upwards to a certain value, which is 50%, of course, reaction force here, 50% reaction force there. Yeah. How will it evolve? You will see, if you do the calculation, that you will have a nice linear line distributed from here up to there. I think this is one of the exercises we did in the beginning. Yeah. So you can calculate it yourself. Like this is a shear force distribution. Yeah, shear forces. In this case, indeed, it's a line, linear shaped, because if you look here, if you go as a microbe throughout your beam, you always add on to the same amount if you crawl as a microbe through your beam. So if you always add on or subtract the same amount of surface, you have a linear line. So the integral of a horizontal is a linear, but of course not horizontally, under a certain angle. Here, second story, you have a reaction force. In our example, we calculated is the highest at the start point, which is logic because you have to counteract a lot of forces acting upon your beam. Yeah. In mid-length of the beam, we ended up with a negative value, meaning that somewhere in between here, we need to cross 0. Yeah. You end up again at a force equals RB, because here you will counteract and you will go to 0. In between, it will be a curved value. You always add on to surfaces. If you're a microbe crawling onto your beam and you go from left to right, there's always a surface that you end up to if you take the integral with a value which is not the same. It's always a different surface. So it means that it's not linear, it's non-linear. So you have a non-linear curve here. It's a curve, not a line. You have to draw it as a curve, or you mark it with colors. Yeah. Upon the exam, I tell you to do it clearly, or you just mark it with colors. You do red or blue for linear and green for nonlinear, as you like. Yeah. And this is the shear forces for that case. If you go for bending moments, you have to keep in mind 0 at the start, 0 at the end of your forces. Where you have your 0, you have your maximum bending moment. In this case, it will be somewhere located here. What happens in between? Again, the surface always adds on. But it adds on with different value. It's not always with the same amount that your surface becomes bigger, bigger, bigger. So it means that you get a curved line. It's not always the same. Then you need to subtract the surface because this is negative. This one is a positive surface. If you're a microbe crawling over your beam, the value here you have to subtract is always bigger, bigger, bigger as you crawl as a microbe through your beam, meaning that it's not a linear but a curve. Exactly the same story here, but only your maximum will not be exactly mid-length of the beam, but it will be somewhere here up front. And then you have a same story, nonlinear bending moment curve. And that you need to be able to draw as well. You can calculate points, interconnect points, but it's good to reason logically what happens. And yeah, a bit of an insight into surfaces, what happens, an integral in a way is useful. Yeah, that's why your course of mathematics are useful in this case. Yeah. For some of you, like to reason with integrals, or you just sum up as surfaces and you crawl over your beam and you see all the surfaces that you need to counteract, and you just add it on to, and then you see that it's linear or not linear. If it goes higher or lower, always with the same amount or not the same amount, is the distinguishing between linear and nonlinear curves. This is clear, or somebody still has a problem with this? Clear? Okay, good. And that philosophy you have to apply to all exercises. Yeah, it's all the same. It always comes back. And that's also nicely explained by somebody else in the video that I gave you the link through Blackboard. That is also nice to see it in a different way. Perhaps it might be useful. What we will do today is exercise number 2 of your examination. Exercise number 2 of your examination is actually similar to a vessel. So we will consider a vessel as an even keel. You all know what is even keel, yeah? A simple beam divided into cargo holds. Some of the cargo holds will contain cargo. Some of them will not contain cargo. And you need to be able to reason the shear force and the bending moment values, as well as the curves as we just did now. So actually it's exactly the same exercise, only instead of a beam, we use a simple even keel hull of a vessel. Yeah. Now I will go first, I will leave this representation and I will go straight to the here, share. 1 second. Here we are. So this is what we all did. That's all your question number 1 upon the exam. And we go now to question number 2. And question number 2 implies the following. This. Yeah. I'll go straight. Actually, what I will do, I will go straight to an exercise. Yeah. But what this represents actually is a part of a vessel. Yeah. With holds of 10 meters in length. Yeah. So what do you have? This here. Something like this. So you have a vessel. Simple beam considered. Even keel. Yeah. hold number 1, number 5 in this case are empty. Hold number 4, hold number 3, hold number 2, they're filled up with a certain amount of cargo. Yeah. Some might see already that you can compare this problem in a way with what we have seen so far. How do you have to see shear forces? Shear forces, again, you have to look as the sum of all the forces acting upon the beam. So you see here at a certain cross-section, at a certain position along your vessel. Yeah. Let me see if this works in the meantime. Yes, it does. So consider yourself as a microbe somewhere at a cross-section, in this case, visualized by the cross-section AB. What are the shear forces at AB? The sum of all the forces acting upon the beam, either calculated from right to left, or you can just turn your back and calculate it from left to right. Again, the value will be exactly the same as you had with the calculations we did before with the simple beam. Yeah, it's just the sign which might be different depending on your sign convention. But for the rest, it's exactly the same. What do you do with the bending moments? The bending moments is the same principle. So you put yourself at the cross section where you want to calculate your bending moments. You look at all the forces acting upon, and you sum up all the moments. So the force F1 multiplied by its respective arm, force F2 multiplied by its arm, and F3 multiplied by its arm. If you sum them all up, you have the counter force here, which should be the same because the sum of the moments should be equal to 0 eventually. So you need to counteract all those moments. And that are the bending moments internally calculated on basis of the external forces. Yeah. So again, you need to visualize all the external forces in order to be able to calculate the internal ones. Yeah. Shear forces, bending moments are the internal reaction forces on basis of what happens externally. Exactly the same story as we did previously. Yeah. Okay, now how do you go here into this translation of this exercise? What do you see? You can compare it to a simple beam. Yeah. Okay, I will leave this and I'll go straight to the presentation. 1 second. Stop sharing and I'll take a blank document. Those who, everybody has the course at hand somewhere. If you do not have it, please note now the exercise and I will explain it in a second through a whiteboard. Yeah, how you need to solve a question like this. So far, so good. Okay, 1 second. I will go here. Come back to you. Here we are. Whiteboard. There we go. So what did we have? Yeah, we had a hull. In case it was. I thought it was solved in the meantime. No, not yet. Why? Up in front. Okay, let me draw a box. Rectangular shape like we have in the exercises, and I will subdivide it by lines. Yeah. So we have here hold number 5, hold number 4, hold number 3, hold number 2. Okay, division is not correctly fully, but this is hold number 2 and hold number 1. Upon the exercise, hold number 5 is empty. Hold number 2, you have cargo. Hold number 3, you have an amount of cargo. Hold number 2, you have an amount of cargo. Hold number 1 is empty. Yeah. In hold number 2, you have an amount of 2,000 tons. You can calculate, if you like, to newtons, but it's not necessarily for me. You can express, as we're all located on the planet Earth, you can keep ton. But that's up to you. If you want to calculate it to Newton, be my guest. Here you have a value of 2,000 ton and empty. Yeah. The length of every cargo hold is mentioned as being 20 meters. So the entire length of your beam at the end is 100 meter. Yeah. So you have 100 meter, and every cargo hold individually has a length of 20 meters. Good. Okay. You see here rectangular forces. You can translate those rectangular forces to resultant forces. So you have a resultant force at 30 meters here of 2,000 ton. This can be translated to a rectangular force at 30 meters of 2,000 ton. This here, the cargo in this hold is 30,000 ton. You can translate this as a cargo here at 40 meters of 3,000 ton. You can translate this cargo to a resultant force at the location of 20, 30, 40, 56, 70 meters. Yeah. You see nearly a beam appearing with point loads. But there's one more question. Do we, by making this diagram, take into consideration all the forces acting upon the beam, or do I forget something? Static forces on a vessel, is it only the cargo considered? When you just have a structure like this, filled with some tanks, the buoyancy, correct, you have the buoyancy force or normal forces if you like, correct, normal forces, the reaction forces of the floor, but it's not the floor, it's the sea. So you have the buoyancy, indeed, you need to take into account, and the Archimedes force, you can call it that way as well, as you like. So indeed, your vessel is being carried by the water, and the water pushes upwards. That's the reaction force of a vessel. And that's a big difference, of course, with a beam who is suspended at 2 points, like simply supported. Here it's carried by the water over the entire length. Yeah. What else do we forget? There's one more thing, which is considered as a static force. If you look at the water displacement of your vessel, which is representative for the entire weight of your vessel, does it only include the cargo? What else? What is the total weight? The weight of the vessel, indeed. Okay, in this case, we neglect persons and food and drinks. It's just a structure with cargo. But the weight of the vessel itself is important too. It's also a load, as considered as an external load acting upon the structure. It's just the weight of the vessel itself. Yeah. And if we go and look into the exercise, then you see that it mentions that you have to consider and illustrate simple beam even keel hull with a displacement. You all know displacement is water displacement, buoyancy force, yeah, which minus the cargo weight, minus the cargo, minus cargo equals what? 2,000 ton is mentioned in the exercise. That's what is mentioned. The displacement minus the cargo weight equals 2,000 ton. Meaning the weight indeed of this barge, or if you like, you can call it light ship, LS, equals how much? The cargo weight plus 2,000. Indeed. So the cargo weight equals, no, not 7,000. Huh? Your light ship, yeah. Wait, 1 second. What did I say? So the displacement minus the cargo is 2,000 ton. So your displacement, excuse me, displacement is 2,000 ton plus a cargo. Yeah. So what do we have? 2,000 ton is what? It's your light ship, huh? your displacement equals 2,000 plus the cargo, and the cargo weight is in total 3, 4, 5, 6, 7,000. So the cargo weight is 7,000 ton. You just sum up here the vectors, which is 2,000, 3,000, 2,000, which is 7,000 cargo in total. Yeah. The light weight of your vessel is considered to be 2,000, but the sum of both gives a displacement. Yeah. So the buoyancy force equals what? The displacement equals 9,000. Correct, Tristan. That is your buoyancy force, is 9,000. 9,000. Now, we're going to make an assumption. We're going to make two assumptions in a way for all the exercises. We're going to make the assumption that your buoyancy force is equally, uniformly distributed over the entire length of your beam. We will also assume that your light ship, in this case 2,000, is also equally uniformly distributed over the entire length of your beam. So if you cut your beam into pieces equal to the entire length of your cargo holds, then you can say that per cargo hold, you have a buoyancy force of 9,000 divided by 5. Yeah. Or what else? You can also say that your displacement or your buoyancy force, 1 second, where do it might equals 9,000 ton in total, or equals what? 90 ton per meter. As your vessel has a length of 100 meters, you can say that the buoyancy force, water displacement, equals 90 ton per meter. Yeah. Your light ship, which equals 2,000 ton, yeah, equals 20 ton per meter, or 20 ton per meter. 1 second, 20 ton per meter multiplied by a length of 20 meter hold equals 400 ton per tank. Yeah. Here, the same with the displacement. It's 90 ton per meter, so per tank it's 90 ton per meter multiplied by a length of your hold 20 meters equals how much per tank? 1,800 ton per tank. Everybody understands this part? Yeah, it's just a basic plus and minus. Yeah. So how do we put this in our drawing? Into our drawing, we will add it as a 1 second. See if I can play with colors. Should be possible, I guess. Drawing. Thickness, no. Opacity, no. Fill color. Okay, let's put an additional vector here. Oh. It only does the outside. That's not the idea. Ah, there we go. That's what I want. Okay, so we have here a Am I the only one suffering with those things? Or do I have colleagues we have the same problem? Drawing? Oh, no. Duplicate. Okay, then we will keep it just in blue if he doesn't want to. No, I'm sorry. We have here a value. Ah, Somebody who knows how to do this, who can help me out? One of those moderators present? I want a line. I have a line. I have a drawing. I have the same problem as I had before. I do not know why. Okay, it doesn't matter. I will restart here. Everybody noted the 400 ton per tank? Everybody understands the 400 ton per tank? And the 1,800 buoyancy force? You got it? Because then I will start a new one in order to solve my problem. I hope so. Wait. No. Okay. No, my pen is linked apparently to the zoom in and zoom out. Apparently, one way or another. No, neither. Okay, I will just stop this and start over because it's getting on my nerves. Clear. Drawing. There you go. So we have our beam. Yeah. We have our holds 1, 2, 3, 4, 5. We have here a cargo weight acting downwards of 2,000 ton, cargo weight of 3,000 ton, 2,000 going downwards. What do we add on to? I'm not going to play with colors anymore or I'm getting frustrated. We have here, what I can do is mention the values again. 2,000. We have here 3,000 in the middle. 3,000. We have here 2,000 so far. 2,000. There you go. 1 0 forgot. Then what do we have to add on to? Going acting downwards is the weight. And the weight, as we told you, you can see as a resultant force per cargo hold of 400 acting here. We add on to 400 here, 400 here, all as uniformly distributed loads here as well. And here another one. Yeah. I'm going to with you 400 light ship, 400 again here, 400, one more time 400, text 400, one more time here, 400, and one more time 400. Yeah, you have time enough to make the drawing yourself in the meantime. Huh? No excuses. What is acting upwards? Buoyancy force per cargo hold going upwards. 1,000. Moderators, I hope you're not intervening, huh? Because otherwise it's a complete mess. And this is another one going upwards, and everyone having a value of 1,800. Here as well, 1,800 again. You see what is happening in the meantime? Are you able to calculate now shear forces at every part along your beam? I guess you are, huh? Which is the sum of all the forces acting upon, whether you're looking from the right or from the left, does not matter. Yeah? Doesn't And one more time. There you go. Yeah. So upon the examination, I will not make your life too difficult. And I might just ask to calculate shear forces and bending moments at the intersection of every tank. So meaning in this case at 20 meters, 40, 60, and 80 meters. Yeah. Which is easy. Yeah. So if you put yourself, for instance, here at this spot at the cross section at 20 meters, how do you calculate your shear forces? Here at the cross section of 20 meters. If you put yourself here, you sum up all the forces you encounter from left to right, which is 1,800 minus 400, which is 1,400. That are the shear forces at 20 meters. What are the bending moments at 20 meters? All the forces multiplied by the respective arms. Now you're going to tell me, yes, madam, but okay, all those forces, it will become a complicated exercise. I agree. If I were you, I would simplify it. You can simplify this model easily. How do you simplify this model? By per tank at mid-length, you will calculate the resultant force. Yeah. So meaning that the resultant force, taking into account lightweight, cargo, as well as buoyancy, you can use as a representation of your simple beam. So it means that here you have a force acting upwards of 1,800 minus 400. Here you will see you will have a resultant acting downwards of 2,000 plus 400 minus 1,800. Here you will have a resultant force going downwards because 3,000 plus 400 is much bigger than the counteracting 1,800. Here you have 2,400 minus 1,800 acting upon your beam. Here again, you will have a force acting upwards. Yeah. So I will just put the values next to it. You can calculate with me if I'm not mistaken. Here you have at the end in symmetry 1,400 acting upwards. You have here acting downwards. How much, please? It's a simple calculation. 600, I guess, if I'm correct. Please correct if I'm wrong. Yeah. Yes, thank you. Here we have in the middle is 1,000 more. So we have 1,600. And here we have as a resultant, we have 600 again. Yeah, because it's the same there. A little cross-check you can easily do. The sum of all the forces vertically should be equal to 0, which means 1,400 2 times acting upwards should be the same as all the forces acting downwards. Simple cross-check, do it, and then you know if you're in the good way calculating, and it's correct indeed in this case. Yeah, it's a simple cross-check. And now it's more easy to calculate the shear force and the bending moment. Suppose now you would like to calculate the shear forces at a location. How do I do this? No. At the location of 40 meters, for instance, it equals how much? Who can guide me through? How would you calculate the shear force at 40 meters? The sum of all the forces you encounter, which is equal to what? 1,400 minus 600. 600. There you go, indeed. Yeah. So indeed, it's equals to 800 tons. How do you calculate the bending moments at that location? The bending moments at 40 meters equals what? The same forces, but multiplied by the respective arms, taking into account the sign convention. So clockwise, we take as negative, minus, yeah, 1,400 multiplied by its respective arm, and that's how much? How much meter? If you locate it at 40 meters, 30, thank you, 30 meters. The other force will be in the opposite direction, so we take it as positive in this case, and it's 600 tons multiplied by 10, half of the tank, of course, as it's close by, 10 meters, and then you can calculate your moment, which is expressed in this case in ton meter. 18,000, okay, thank you, I suppose it's correct. There you go. Why a question mark, Jules? You send a question mark, why? You ask if it's correct. People, please calculate it. If it's correct, the bending moment at 40 meters, is it correctly calculated by your colleague? You're not sure 100%. How did you calculate it? It's not correct. Who has another value? Who has here another value? 30 multiplied by 6. Why? 600 multiplied by 30. Why by 30? Why do you take 30? Position yourself. You always have to. Yeah, wait 1 second. We'll fill it in later. You have to position yourself, Jules, at a location where you want to make your calculation. So you have to imaginary place yourself here. So this is you. 1 second. It doesn't want. So you are located imaginary here at 40 meters. Yeah, this is your location. You're a microbe at 40 meters and you're looking upon all the moments acting upon and you add them onto, which means 1,400 multiplied by its respective arm. Wait 1 second because it zoomed out again for me. So you have this 1,400 multiplied by this arm, 30 meters. And you have 600 multiplied by this arm, which is 10. But you have to subtract them from each other because there's a difference in sign. And then what do you end up to? At 40 meters? Gillian, please recalculate it for me. What's that, Simon Getty? Yes, that's the value I would like to have. 36,000. So if you do 1,400 multiplied by 30, and you understood, Jules? Okay, perfect. So always one of the fundamentals is to calculate shear force and bending moment. You are a microbe into the beam. Imagine you on the spot where you would like to calculate the values and look outside. All the outside forces or moments you need to counteract internally to be in equilibrium. That's the basis. So you are a microbe located at 40 meters. You look upon all the external forces acting upon the beam and you need to counteract to stay in equilibrium. You need to counteract. Action is reaction. So in this case, for shear forces, you have the 1,400 minus the 600. You have to counteract at 40 meters. Yeah. If you're located one step further at 60 meters, for instance, then you need to counteract as a microbe. All the external forces you're looking is 1,400 minus 600 minus 1,600. The same principle, but then for the moments multiplied by the respective arms. Yeah. Gillian, you found your problem in your calculation? Yes? Okay, super. So if I go back now to the presentation, then you will find the solution, I guess. I think I gave the solution in the presentation somewhere or have it. Certainly. Yeah, there we go. 1 second. Share screen and audio. There we go. So if you here see the solution of the exercise, yeah, then you will see the value of 36,000 reappearing of bending moment at 40 meters. Yeah. A drawing is also made of shear forces and bending moments. As we all have horizontal distributed forces, the integral will be linear lines. So your shear force are all linear lines. The integral of linear lines, which is at a certain angle, gives you nonlinear curve bending moment. Yeah, so you see it reappearing. Again, what do you see reappearing? When your shear force equals 0, your bending moment will be at its maximum point. So you have to calculate, in this case, at mid-length of your beam, the bending moment, if you like to know the bending moment. So then you need to position yourself as a fiber. Yeah, here it does work, apparently. You need to position yourself at the fiber here, mid-length of your beam, if you would like to calculate your maximum bending moment. Yeah, which implies, yeah, for that cargo hold, number 3, you only have to take into account half of the cargo, half of the light ship, half of the buoyancy force taking place here at 1/4 of the length of the beam, meaning in this case at 5 meters from you. So if you want to calculate this maximum bending moment in values, your simplified drawing will look like this. 1 second. So you have 0 meters. Let's say this is a 20-meter cargo hold. This is the 40-meter. This is the 60. But we want to know the bending moments here, because we know the max is mid-length. It's all in symmetry, huh? So you know that it's in the middle. Your vessel is sagging, and the middle is indeed where you have your maximum flexion. Yeah. So what did we calculate before? What was here the resultant force? I do not recall by heart. I think it was 1,400 ton. Correct? Correct or not correct? I think it was here 1,400 ton. You have all the notes at hand. Huh? I don't. Yeah. Here we had, how much was the resultant force? 600 ton, if I recall well. If we consider the full length of this cargo hold, the total resultant force was 1,600. But we do not have to take into consideration the entire load. We have to take into consideration only half. Huh? So if you look up here, if you're a microbe in mid-length of your vessel, you only take into consideration one end, which means half of all this. So what this resultant is not correct. We need to split it up into 2 forces, of which we only take this part into consideration for our calculations, which is 800 ton. Yeah, 800 ton left, 800 ton right. You can split it up in as much as resultants if you like, but you need to know which simplification is good for your calculation. Yeah. So how do you calculate this maximum bending moment? In this case, your maximum bending moment, this value is obtained by, where am I here? Equals what? The first moment is 1,400 multiplied by the arm, and the arm is how much in this case? What is the arm? Yeah, you have to tell me because I can't see it with the shared screen. I'm sorry. You have to take the mic. 40 meters? I hope you want to say that one. I will check later on, which is clockwise, so I take it as negative. Plus another moment, 600 ton. Distant from you, when you're located as a microbe, mid-length of the beam, you need to counteract, is multiplied by 20 meters. Yeah, plus 800 ton multiplied by how much? You're located at 50 meters. You take only half of the cargo weight into consideration, half of the light weight, half of the buoyancy distribution, which equals then 5 meters. Okay, because here you have a length of, wait, where am I here? A length of 10 meters, half of it, this arm is 5 meters. And if you calculate this, you should end up with this value, this maximum bending moment. Yeah, and that's how they came up to that calculation. Yeah, What else do you find in this course? A bit up front. A bit up front is just to visualize to you that indeed we are talking about integrals. Huh? So if you make this calculation as I do it, you will see you will end up with the same values which are represented here. How do they calculate here the bending moment at 10 meters? They calculate it by the integral. So the integral or the surface underneath the curve. Your shear force here in this case is triangular shaped, going from 0 to 600 tons over a length of 10 meters. A integral is a surface underneath the curve. So it means that it's half of the rectangular, half of 600, the height multiplied by the base. And then you get the same value as if you would follow my example how to calculate it. Yeah, the same they did here. So you have here a rectangular shape plus a triangular shape to come to the bending moments. Two surfaces, they add on to each other. So 10, 300 tons multiplied by 20. And then here they make a triangular shape on top. Plus this, of course, yeah, and here again. Yeah, that's how they do it. But it's up to you. You can use integrals, whatever you like, whatever way you want to calculate it. I leave it completely up to you, but they have only one restriction, and that's the end should be correct. Yeah, it's all up to you to make your calculations by integrals or just a simple example as I did. Okay, then you have an exercise here. Of which the solution is indeed given. Do I have somewhere an exercise that I did not give the solution in the presentation? I'm not clear. 1 second, and you can do it now. No. Okay. What I will do is I will just quit this one screen. And you will have to try to solve it yourself. And in case you have problems, you have to let me know. Yeah, we still have some time left, I guess. Huh? Do we still have some time left? We do, huh? Yeah, we do. Okay, escape. Discard. What I will do, I will quit share screen and I will make you a blank. And we will make an example, clear annotations. So you saw in the presentation, you have quite some solutions, yeah, with indeed the curves added onto, so you can easily calculate it yourself at home. For those who are were present last year, let me take the latest newest exercise you can find completely at the back of your Word document. And I will illustrate it now, and you will have to calculate it for me. Yeah, and we do it here with everybody present. Wait. What is this? Hand tool. I might have found a problem with my pad. No, not yet. No. Yeah. Okay, no. So what we will do, we will take the last exercise. You all have the Word document with you or not? I will draw it anyway. You have the same problem as before, but now you have 7 cargo holds. Yeah. Exercise 26 is possible. You have 7 cargo holds. Yeah. Again, you consider it as a simple beam, even keel hull, divided into 7 pieces. So you have 1, 2, 3, 4, 5, 6, 7. Yeah. It is illustrated like you have an alternated loaded vessel. So we have the uneven tanks which are loaded with cargo, as illustrated now. The even tanks are empty. Yeah. What does it say? It says that your displacement minus cargo equals with the displacement minus cargo weight equals 20 ton per meter. That's what is mentioned. Excuse me, 20, of course. 20 ton per meter is mentioned. What else is mentioned? Every tank is 20 meters. 20 meters is mentioned. There is mentioned that the total cargo weight equals 21,000 ton, alternately loaded in the uneven tanks and equally loaded. Yeah, so it means that every tank which has cargo has the same amount of cargo. Yeah, and then the question is calculate the shear and bending moment values. Minimum at every 20 meters, so it means at every intersection of every tank, and make a shear force and bending moment diagrams and make clear distinctions between linear and nonlinear curves using colors as you like. Okay. How do we start? Somebody? How would you start? Tell me. How would you solve this problem to start with? The total length, indeed, you need the total length of your vessel. How much is the total length of your vessel? The total length of your vessel is how much? On basis of the values given, 140, correct? So indeed, so you have, every tank is 20 meters in length, you have 7 tanks, so indeed it's 140 meters is your entire length of your vessel. Yeah, so resulting in here, you have 120 meter, you have here 100 meter, you have here 80 meters. You can do it yourself at home. Make drawings, please. It will help you with your exercises. And then you can reason in the meantime, because I'm not going to do the calculations, but you are. It's up to you. 40. And then we have one of 20 meters here. So at every intersection, I want values of shear force and bending moments, meaning at 20, 40, 60, 80, 100, 120, and 140 meters. Yeah. Okay, this is one thing. We need to make a representation for easy calculation, knowing that we need values every 20 meters. So knowing that we need values at every 20 meters, what is easily done is just make a visualization of the external forces per section of 20 meters. That's the most easiest way, of the most easy approach. Let me put it that way. Yeah. So I'll draw it as a line, your vessel. Yeah. Every intersection, I just put a small thread, and that's it. Nothing more, nothing less. Here we have one drawing. I will do it this way. That's easier. Here we have 180, 100, 120, 140. So what is the cargo weight in every tank? How much have in every tank? And how did your colleague end up with this figure? We have cargo weight. We know that over total cargo weight divided 4 cargo. So that's easy. We need to take it. You don't think it with my cell phone. Then it means that yes or no. Do you hear me better now? Tell me something. Somebody. Second. One more. That much. Okay, I will solve it. I will put on my hotspot. Allow others to join. I switch off the Wi-Fi here. Hotspot, allow others to join. Settings, because it's a new, it works now. Don't ask me. Here. Not connected, not connected. Connection possibilities. Your phone. Your no. 1 second, huh? Bluetooth. Get started. It's not yet better. The connection. 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 Perhaps I have to disconnect first with the Wi-Fi to get the Bluetooth possibility. No, doesn't work. Okay. I'm afraid we have to try it this way. No, still choppy for you? For all of you, I guess, then? Better and better. Okay, let's hope, fingers crossed, that we can still continue up to the end. Okay, now it's better, it's better. Okay, fingers crossed. Let's have the cargo force is considered as an external force. As you know, we also have to take how much per tank? drawing. Light ship per tank. Light ship is considered as uniformly distributed, equally divided over the entire length of your vessel. 400, very good. It's 20 tons per meter. Every tank has indeed 20. So we have here 400. And then we continue. I'm not going to put it constantly all over. You just have to copy on it. So you just copy further and further. You have 400 per tank, huh? As a resultant force taking place, acting mid-length. What else do we need to take into account as a force? What else? What is thinking? So we need the buoyancy force per tank acting upwards. Yes, indeed. Should be to 3,400, if I'm not mistaken. Per tank, buoyancy act. A resultant force represents, yeah, every part. I just will for the first two tanks, but it's the same all over. Start idea. By just summing up, not mistaken, depending on how you put the sign this one, the one acting upwards, down, up. Okay, no problem, Jonas, because you need to follow what I'm writing down. Okay. Waar vind ik dat? So, and then you continue because it's always coming back the same values. Yeah? So knowing this, you're able to calculate all the shear forces and the bending moments at whatever position along your vessel, huh? So imagine, for instance, you want to calculate shear forces and bending moments at 60 meters, yeah? So meaning that you are imaginary, located here as a microbe at 60 meters, you're here positioned, and you're looking at all the forces acting upon the beam. You make the sum of all the forces. So what do you have as a shear force at 60 meters? What is your calculation? I'm not sure. The shear forces, if that's correct. Everybody has the same value? Yeah, that's correct, Gillian. Simon, please recalculate. So you have to do, I will put downwards as negative, 2,250 plus 3,000, the next force you encounter. Yeah. Minus, again, 2,250. And that equals, indeed, minus 1,500 ton. That's your shear force at 60 meters. Yeah. Please do the same thing for the bending moments at 60 meters. What is your answer? I will do it in the meantime as well, but I think I have to press enter before you see it. At 60 meters, recalculate, Tristan, please. There's a small error. Unless I have an error, of course. Huh? That's always possible. 50. Everybody has the same, or somebody has a different answer? Somebody else? Who can help out, please? Yes, indeed, Antoine. Correct. So this is how you need to calculate it, huh? If you look at the bending moments, good, Loïc, excellent. So you need indeed visualize yourself as your microbe and look at all the forces acting upon. The forces acting upon is, in this case, you have 2,250 at the distance of this arm equal 50 meters. 3,000 multiplied by the respective arm, 30 meters. And 2,250 multiplied by the respective arm of 10 meters. Taking into account the sign convention clockwise, counterclockwise, you will indeed finally end up with 45,000 ton meter. Don't forget your apples and pears. Upon the exam, you always have to mention whether it's ton or newton or meters or millimeters, whatever. Yeah? That's how you calculate the bending moments. That are the value calculations. And then you just still need to draw the evolutions of shear force and bending moments. Yeah? Somebody who wants to try out? In this case, I think the solutions are given, huh? Somewhere. Or I didn't ask. Possible. Did I ask it in this case? Yeah, I did. Yeah. Okay, somebody who tells me, where do you think the maximum will be located of this exercise? In shear forces and the bending moment values? Where do you think that will be the maximum bending moment located? Where will it be located? it's in full symmetry, it's quite easy, huh? It will be perfectly in the middle. Midships correctly, it's perfectly in symmetry. So it will be, it means indeed midships, huh? In the middle of your vessel. Yeah, correct. And if you want to make the drawing, you will see that your shear forces will evolve like going down, 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 and then they will go up, and then they will go down, and you will somewhere, you will cross, for sure have a 0 shear forces in the middle. Yeah. If you have zeros in between, yeah, you might end up with curves like this, huh? And then if you have like those crawls, it might give you more and multiple 0 points. Now, to give you an example, I think I have some examples in the course. It's easier in the course to make reference to because it's clearly drawn. Screen. 1 second. Share. I hope I still have the PowerPoint up. No, I don't. Let me take this one. Takes a few seconds. Some examples are given in the course. How to draw them nicely. Here, for instance. Yeah. So you see indeed evolutions of shear forces and bending moments, and the maximum as it's completely symmetrically, you see indeed that it's perfectly located in the middle, and it will always be in symmetry in a way. Here you have the same thing, but this is what I mean. You have multiple 0 points, which can happen, but then you have bends and multiple maximums or respective minimums. It depends on how you calculate it. Yeah, and this is in this case, of course, valid. So you have maximums here, a minimum, maximum. It depends on how you look at it, and here as well. And this is a nice example how to draw this one. Yeah, it's similar. But that's a bit of a reasoning, and then you need to place points. Upon the examination, you do not have to make it really 100% correct. A sketch is enough, huh? But in the sketch, you must clearly indicate where are minimums, maximums, 0 points, and where is linear, nonlinear. So you do not have to make a detailed on scale drawing. It's not necessary. A sketch is enough. But the sketch has clearly indicate where you have zeros, where you have maximums, minimums, what is linear, what is nonlinear, and that's it. Yeah, and you do have some examples. Okay, so this is question number 2 upon the exam. So you have a beam simply supported or in a wall, but most of the time it will be simply supported. You need to calculate shear forces, bending moments, and make the drawings. That's one exercise. Second exercise is like this. You have a barge in a few holds, even keel. Start from the idea the buoyancy as well as the light ship is equally distributed over the entire length. Make a simplification, make your calculation of shear forces, bending moments, and make drawings like this. That's your question number 2 for exercise. You will have 3 exercises. So 1 and 2 is known in the meantime. Do you have questions related to this type? But you have to make them at home. You have to practice, practice, practice. And we will do a recap with 1 exercise of each kind the 9th of March. Yeah? For those who are present, we solve the questions and we make from all the extra exercises, we will make 1 additional one upon the recap on the 9th of March. But I will base myself on the present exercises, huh? Because those who are not present, because they know how to calculate it, fine, huh? So I will base myself on the available exercises, or if I put an extra one, it will be placed on Blackboard, so everybody has access to what is given as exercises. So that you do not benefit from being present or not. Only those who have problems benefit from being present on the 9th of March. Yeah. Or those who want to recap is always good, of course. But it's not mandatory. I will not give extra exercises or whatever. It will be nothing secret for those who present benefit. No. You have the content, and those who have problems, they come the 9th of March, of those willing to come. And in case there are extra exercises, it will be placed on Blackboard so everybody has access to the extra exercises. Okay, questions? Something you want to be repeated? We still have 10 minutes left. So it's up to you to indicate if you need more help with something. I know it's a bit of a self-study. You need to make and practice, but that you have to do yourselves. I will... Okay, wait. I will stop this because I'm still sharing. What I will do, I will remain here behind my PC.